Hi, I'm Enrique. We created a heat exchanger for our thermo project. This is really technically relevant because of so many things such as engines, computers that we have to cool on a daily basis. We specifically used water to demonstrate its abilities as a coolant.
Hi, I'm George Kirkendall, and I'm just going to explain the system today. Here's our heat exchanger, right? We have this reservoir 1, reservoir 2. And so, first off, I'm going to define what the system for the calculations will be. So we're going to define the water as our system, so that will include everything within the reservoir, and then also within the tubing. So basically, we can eliminate the mass flow that way. Okay, so there's a couple assumptions we need to make before we go over these calculations. The first assumption is that both fluids are incompressible, and that's mostly just because the specific volume of fluids in general changes very little, and the temperature range that we're working with over this experiment is actually quite small on a thermodynamic scale. The second assumption is that the specific heats are constant. Once again, that's because the thermal range is quite small, and the water only changes about 0.20 kilojoules per kilogram Kelvin, so it's not really important. And so the third assumption is that we have a closed system, and that's just because there's no mass flow outside of the system that we defined for the water. And the fourth assumption is that we're in a quasi-equilibrium state. That's basically because the amount of mass that's in this tube that's going to be a different temperature from the rest of the reservoir is actually quite small. It doesn't affect the total energy too much. And because of the movement of the water, it will equalize quite quickly. The fifth assumption is that there's no heat flow at the environment. Realistically, there's going to be some heat flow, especially out here when the tube is between the two reservoirs. But we kept both of the liquids within styrofoam containers, and it's really not too big. So those are our assumptions. So for the energy balance, obviously we start with the first law, and then expanding that out, we get our heat flow in, then our work's in, and our energy flows in, and then obviously out. And basically, because this was a closed system, our energy flows are going to go to 0. And then also there's nothing doing any work in the system's not doing any work, so those are also going to go to 0. And because for the duration of the experiment, the water is the T low and it never goes above, oil's T high, heat flow is only one direction, so there's no heat flow out of the water. So basically we just get reduced down to Q in, and so obviously this is all to 0, this is all to 0, and just the Q in, and the Q in is equal to the change in energy of the system, which is our water again. And expanding this out, we have a constant specific heat because, once again, the temperature range is quite small on a thermodynamic scale. So we just have the mass times the specific heat, which is obviously on a per mass basis, times T2, final temperature of the water, minus T1, initial temperature of the water, and then we'll give the total energy flow into the water.
Hi, how are you? My name is Valentina. I'm going to be presenting the entropy balance. So first of all, we have the integration of Q net divided T. That's going to be equal to the change of the entropy in the water. After that, we have the change of the entropy of the water minus the change of entropy of the oil minus Sgen, that's going to be equal to 0. With that being said, we have Sgen equals to the change of the entropy of the water minus the change of the entropy of the oil. And then we're just going to open up the formulas. And here we have the mass times the specific heat of the water times ln T2 divided the temperature of the water minus the mass of the oil, the specific heat of the oil, times logarithm of 2 divided the T oil. That's going to be equal to Sgen. And from where we got these formulas is from here. So we have that the specific heat as a function of T, and then we have the differential of the temperature equals to the C average, that's the specific heat, times logarithm divided by the T1 and times 2. And this is because we have an incompressible substances.
Hi, I'm Matthew. So using the data that we collected from our actual experiment, we were able to calculate the specific heat of the oil, knowing that the energy in from the water is equal to the energy that's lost through the oil. We were able to set them equal to each other, and then just with some algebra, derive this formula, and then it's just plugging and chugging. Given our known values, which we found during our experiment, we were able to plug in all of these and our masses into this equation and find that the specific heat of the oil is equal to about 1.1 kilojoules per kilogram Kelvin. We're also able to find the equation for the entropy generated, knowing that it would be equal to the entropy that is gained from the water and the entropy that is lost through the oil. So again, just plugging in all the values that we've already found, we're able to find that the SGen is equal to 20.7 kilojoules per kilogram Kelvin.
Here we have the two reservoirs, the tubing, the canola oil, and the thermometers. We use these to create the heat exchanger. We attach the thermometers to the top of the reservoirs so that they are touching the water but not submerged in them. Our calculations were specifically for the water in the reservoir and the tubing, but we did use an exact amount of canola oil. Everything inside the reservoir was taped down to avoid any moving at all and to have as exact results as possible. The hot oil was added as close as possible to the first moment that we started recording so that the temperature would be as high as possible and we could see more clearly the trend of the results, because as the temperatures approach each other, they change in temperature, become slower and slower.
Okay, a minute has passed. Let's see. Okay, that's. Is it 60?
Yeah, it's 60. 148. 60 and 148.
Okay, it's the same. 160, 61, and 143.
Oh my god. The water's like not changing at all.
Yeah.
Hi, I'm Matthew Lopez, and I will now discuss the relevance of heat exchangers to current technologies.
A heat exchanger is a device used to transfer heat from two or more liquids. It works for both cooling and heating processes. Our project is a basic heat exchanger using water to cool down oil. Heat exchangers are extremely relevant and vital throughout the world. Heat exchangers are used in various industries, such as refrigeration, space heating, and nuclear power. One of the most important uses of heat exchangers moving forward is as a heat sink within a computer. A heat sink is a type of exchanger which acts as a passive heat exchanger that transfers the heat from an electrical or mechanical device by using a fluid, which then allows the device to be cooled down. They are most commonly used for cooling down the central processing units and the graphics processing units. In today's world, we are trying to make our processors smaller and smaller while also making the units more powerful. In order for this all to work properly, the units will also need to be cooled down at a more efficient rate to ensure that they do not overheat. Heat exchangers are vital and will continue to be vital as technology continues to advance.